back. I think that's
okay. Welcome, Tana, Nicholas, and Michaela. Thanks for coming. So this is the week 9 webinar. It's hard to keep track of where we are. We're getting close to the end. And let me talk about what we're doing today, and let me get to share my screen. Okay, so the plan today is I'll start out with Q&A. I'm just talking about what we're doing. And then we're actually changing gears. We have spent the last several weeks talking about how to analyze quantitative data and how to analyze data that came from a yes/no question. Now we're changing that completely. So what else is there besides the yes/no question and quantitative data? So what else is there besides those two? Yeah, there's qualitative. So today is a day where we can talk about qualitative data. So if you have a survey question where the answer is not yes, no, and the answer is not a number, then it's qualitative data. And the idea is, yes, we can still handle it. And we're going to have some ways of handling it. And one of the ways is going to be looking at what's called goodness of fit. So we're going to look at a goodness of fit test. It's called a chi-squared goodness of fit test. And chi-squared, we've seen the normal distribution, the t distribution, the uniform distribution, the binomial distribution. Well, it turns out when you're dealing with these qualitative data kind of questions, there's another distribution we're going to use. And that distribution is called the chi-squared distribution. The mathematics is way too hard for this class. So I'm not even going to pretend to explain the math behind it. Maybe I'll show you a picture. Even Braulio couldn't handle the math, Braulio. Okay, just trust me. You need graduate level kind of stuff. It's brutal. So we're not going to do the math of it, but you should get used to the fact that you get a test statistic and a p-value, and that's what we're going to get. So we're going to have a goodness of fit, and goodness of fit is to see whether something fits a distribution. And it turns out there's going to be a few types that we'll look at. One is to say, well, is it uniform? Is everything the same? Okay, and if everything's the same, then that means it's uniform, or maybe we suspect it's not. Another is it the same as what we predict it to be? So a good example of that is to find out, for example, do college students at community college fit the distribution of people their age in terms of race? Now, the survey question you ask is, what is your race? And you might say, I'm Asian, or I am Hispanic, or African-American, or Caucasian, or whatever. It's a word. And you want to find out, well, if you look at the distribution of races at the college, is that the same as the distribution of races for the community? And you'd like it to be. I mean, that would be a good thing. So the question is how do you figure out if it is when you have a sample? And we'll learn how to do that. So then the other is other distributions. And this is something that we did a while back. We talked about you had to make an assumption often when you calculate a distribution. An assumption is that you had a normal distribution. Do you remember that? And kind of we did a weird way of doing it. We drew a histogram. We said, yeah, it looks kind of bell-shaped, or it doesn't. Well, it turns out there is a statistical test to say if there's statistically significant evidence that it doesn't fit a normal distribution. And that test is the goodness of fit test. It turns out there's more advanced tests that people use that are past what we're going to be doing in this class. But there's a simple test called the goodness of fit for that. Then we're going to do what's called the test for homogeneity. And that's similar to the goodness of fit in that the goodness of fit looks to see, does a distribution that you've sampled fit some known distribution? Well, sometimes you want to say, well, you got two different groups and two samples, And you don't know their distributions in the population, but you want to find out, are they the same as each other? So that would be things like, is the distribution of majors that students have at the college, is it the same for men and women? Or are the majors that people have gender dependent? Okay. And it'd be nice if they were the same, but you can do a statistical test, to find out whether men and women tend to take the same or have the same major when they're college students. And the test for that is going to be, it's another chi-squared test, same distribution, but it's going to be called chi-squared test for homogeneity. And then finally, we're going to be doing something called the chi-squared test for independence. And that is all about saying, well, you have two different variables. So you might ask someone two questions, and you want to find out, are they independent of each other? Sometimes we'll say, is one a factor of the other? So for example, you can have one being race and the other might be major. And you want to say, well, if you know what someone's race is, does that give you an idea what their major might be? Or maybe they're completely independent of each other. And we've talked about independence before, but only for one answer of one of the questions to a specific answer of the other question. Here, we're looking at all of them combined to say, is there a dependency in the two categories? So that's the plan today. The good news is that most students find this one of the easier weeks. So most people like that. Still, there's work to do. And let me talk about what we just did and what's coming up. So what we just did is the exam. And I will let you know, I have graded the exams that were taken for Thursday and Saturday. So those are graded. And I'm not sure, I'm just looking through the list. I don't know if any of you, hopefully you all got my comments, because it didn't work last time. So this time I'm totally doing it differently, where I'm not doing comments per question on the question itself. Now I'm doing comments on the comments section on the test, which is different. And hopefully you get that one, because for some reason in exam one, it didn't work. And I don't quite understand why. And I asked for help and the person never got back to me. So I'm bummed. So I'm trying something different. And I'm looking to see if anyone took it. Did all of you take it Sunday? If you take it Sunday, then you don't know anyway, because I haven't graded the Sunday one yet. It takes a long time for me to write these comments down. There's a lot of problems, a lot of students. So, each comment is sentences, and we're talking about several hundred sentences for me to write. And it does take many hours. So probably my guess is by the end of the day tomorrow, I'll be done. I'll do more today after this. And then tomorrow I have most of the day to do that. I want to note another thing that's real important, and that is Wednesday. I do not have office hours Wednesday. How come? Anyone know?
Doctor's appointment.
No, I do have power Wednesday. No doctor's appointment. It's Veterans Day. Yeah, Veterans Day. And I believe in honoring our veterans. Hopefully you do too. And celebrating the holidays. So I am not going to be doing official work on Wednesday. Okay, I might check my email, but I'm probably going to go to Mona Lake and play around. So I don't even know if I'll have internet access most of the day. So I'll check it at night probably. So just a note, Wednesday I'm going to be mostly offline because I'm taking a holiday, and we're allowed to. Okay, it's not my special holiday. It's we all get one. So it's an official college closure, and so just let you know, there's no office hours. Okay, we didn't have anything special going that day anyway, so it shouldn't affect you very much. But if you're wondering why it's taken me so long to get back to you or something, and why I didn't show up in office hours, that's the reason, because it is Veterans Day Wednesday, and I like to take the holidays. Just like Thanksgiving, you can try to get a hold of me Thanksgiving, but no. So we don't have a lot of holidays. Thanksgiving week, I'll be checking my email and stuff, but I don't have office hours Thanksgiving week because we're college is closed Thanksgiving week. is the way we're doing it this year. So are there any questions about anything? And that could be the project. So let me remind you, now is the time to start thinking about the project. So this is project, focus time, because now we're done with exam 2. So for the next week or a couple weeks, project time thinking. So it could be a question about the project, or it could be a question about anything else. Any questions? You can put in the chat box, you can talk, either way. Okay, if there's no questions, then I think I'm going to get and talk about, this is chapter 11, by the way. So we're moving into chapter 11. And I do want to mention something. Chapter 11, we're moving into statistics that is not day-to-day stuff. Now we're talking about statistics that's really used for research. So I'm not going to be able to give you a current event where we're going to calculate we're going to look at some statistics that they calculated in CNN or something, because now we're at the college level at stuff that's only done at the advanced level. You won't see it on the day-to-day stuff. So I'm not bringing in a specific current event where they used a chi-squared test, because you're not going to find that. And in fact, on your this week, there is a discussion post you have to do. And you are going to have to go to a journal. And part of that is because you're not going to find it anywhere else, because chi-squared is done in journals, but it's very common. And I want to remind you, when you do post, do not find an article about chi-squared. You're finding an article that uses chi-squared. So if you just search chi-squared in the title, you're going to find a bunch of things that are chi-squared. So search for other things, and probably by the 3rd or 4th time, you'll find something that uses chi-squared if you look at research articles, because it's very common. Okay, so I'm going to give you examples of goodness of fit that are, kind of fictitious examples that they could happen, and some that I've done myself. All right, so let's look at some questions that we can think about. So let's suppose, and when I say suppose, it means I'm just making it up, just a warning. Suppose a survey was conducted to see, okay, and in fact, I'll even do different than the survey. I'll do my own personal experience. You remember what I did when I turned 21, those couple years? And no, I didn't drink a lot, by the way. Yeah, I gambled, okay? But I gambled to win. It was different than most people gambling. It was not one of those gambling where you have a problem with gambling. They had a problem with me as a thing, okay? But let me tell you what happened. Things were different. Do you remember? Again, it's a different generation, but in that generation, okay, I'm older. Do you know who controlled the casinos? Yeah, the mob. And what they would do is that when they would see me count cards, okay, at the beginning, before they just gave up on me and they realized that I couldn't fall for anything they did, so they just told me they'd kill me. So, but what they did is they'd bring in their special person, and often called a cheater. Okay, so you're in the casinos and playing blackjack, and suspect that the dealer is cheating. In particular, you think that the dealer is getting too many face cards and aces. Okay, and by the way, that is what they did in those days, is they would cheat that way. They do face cards and aces, and I know for a fact because my grandfather was one of them. Okay, he's dead now, so he can't get in trouble. but just let you know, he taught me about this stuff and how to watch it and then I did the statistics. Okay, so you observe out of the 40 cards that the dealer deals himself, we'll assume it's a man, that 7 are aces, 12 are face cards. Actually, let's go, I better not go 40 because that's not enough. Let's go 80 and not make it 7, but make it 11. So 11 are aces. And face cards and 10s, I should say, because they go together. So, and then 25 are face cards and aces. And 10s, right? And the rest are others. So, is the dealer cheating? Do you understand the question? Any questions on the question? Okay, so if you're worried about the dealer cheating, what you do is you count cards and you track how many aces, face cards, and others there are, and you see if it is matching up what you would expect it to be. Now you would expect 1/13 of them to be aces. You'd expect 4/13 to be 10s and face cards. And because there's 10, Jack, Queen, King, that's 4. And then there's 2, 3, 4, 5, 6, 7, 8, 9. 2, 3, 4, 5, 6, 7, 8, 9. That's 8 different others. So you'd expect an 8. So you'd expect 8 out of 13 to be the others. Any questions on the question first? All right. So what we're going to do, and you're used to this, the first thing you always do in hypothesis testing is you say, well, what's your idea? Okay, the idea is what I put in the paragraph, is I think the dealer's cheating. That's my idea. Any questions on that? Okay, then what you do is you write down the null and alternative hypotheses. So the first thing, H naught. Oops. All right, so I want to give you a warning. So let me ask you, when you do H naught and H1 in chapters 9 and 10, how many words do you see? When I ask you to write H naught and H1, how many words do you see? So how many words do you see when I ask you to write H naught and H1? Yeah, 0, okay? In chapter 9 and 10, it's not, no words are allowed. Got it? Okay, when I ask you to write down the null and alternative hypotheses, like I did on the exam for chapter 9 at least, there are no words. Okay, it's symbols. It was like mu equals 7 or p equals 0.26 or something like that. Okay, so promise me that if there's ever a question from chapter 9 or 10 or 12, by the way, then, and you have to write down the null and alternative hypotheses, you don't write any words. Okay, and the reason why I'm saying this is that chapter 11 is all words. So I know that's hard to keep track of, but you need to keep track of that. So remember what's words and what's not words. So chapter 11 is words. And one of the key words, because what we're looking for is to see if the distribution is what you would expect it to be. So the word distribution needs to be there in H naught. So in this case, the distribution of the dealer's cards is the same as a regular card deck, or as the distribution for regular card deck. Any questions on that? Okay, because if the distribution is the same as it is for regular card deck, then you're not going to say the dealer's cheating. You're saying, oh, okay, that's what I expect. Any questions on the idea of H naught? Okay, then there's H1. And the nice thing about H1 is all you have to do, and this works great on computers. So when you're doing a test, for example, you can copy, you can paste, and what do I change? All I have to do is add one word in there. What word do I have to add in? Yeah, not. It's not a greater than, because a distribution is not a number, so you can't talk about a distribution being greater than something. Does that make sense? Right? If you have a normal distribution, but then then you have something that isn't that way, you can't say it's greater than normal. You just say it's not normal. Well, in this case, we say the distribution of the dealer's cards is not the same. So very easy to type. Just copy and paste and stick the word not in. And I want to let you know, it's not, you need to write this in words. It's a full sentence. And I'm going to do the following. This word distribution, what do you think is going to happen if you do not have that word, if you're doing a chi-squared test for goodness fit test? Do you know what's going to happen on your exam if you do not have that word? Yeah, going to lose points. So here's the thing. I want you to make a promise. Put yes if you promise to put the word distribution in both H naught and H1 if you're doing a goodness of fit test on the exam. Put yes if you promise, no if you don't promise. Okay, so I'm hoping this will work. Maybe it won't, but it didn't work last time when I told you something. So maybe if I ask you to promise, you'll actually do it. Okay, because remember, I've been grading the tests. I graded the Thursday and Saturday version. And I did a lot of you must say this in the webinars, and then I didn't see it. So when you're doing, for example, if you're talking about a hypothesis test for a proportion, or you're talking about a hypothesis test for a mean, then you must talk about the population. You must explicitly refer to the population. Do you remember that? A lot of you didn't when you took the test and lost points. And I hate that. I don't like taking points away, but these are things I'm telling you now. Don't forget the word distribution. Okay, so that's the first thing. The next thing we're going to do is we're going to identify the test. And the test we're going to use is called a goodness of fit test. Because we're seeing whether the card deck's distribution is a good fit for the dealer's cards. Okay? Do the dealer's cards fit the card deck distribution? So it's called a goodness of fit test. I didn't make this up, but that's the name of the test that we're using. Okay? And sometimes they call it a chi-squared goodness fit test. But if you write goodness of fit, that's good enough. If you write GOF, I'm happy enough. But you should know which test to use. If you don't know what test to use on the final exam, do you know what's going to happen? If you get to the final and you don't know what test to use for the problems, you know what's going to happen in the final? Yeah, you will fail the final, not just lose points, you'll fail the whole final. So the most important thing of this entire class is to know what test to use or what confidence interval to use. If you can't do that, you can't even start and you won't get anything right. Okay. The funny thing is I got an email this morning from the head of the AP exam. Okay. College Board, they call it. I don't know if you heard them. And they wanted my permission to use my app that I made on what test to use. Okay, it is really a national thing. So I created the app in the world for this, and everyone in the world is using it. It's pretty cool. So before the final, I'll show you. I have a whole app on what test to use app. So for now, this one's goodness of fit, chi-squared goodness of fit. Any questions on that? Okay, so the next thing we probably want to do is decide on the level of significance. And because there's no reason to go one way or another, what's the standard? What's the standard level of significance? You should all know this. This isn't new. 95 is the confidence level. This level of significance, 0.05, 0.05, 5%. So 95 is for confidence intervals. Just to let you know, there are no confidence intervals in this chapter. Okay, we're done with confidence intervals for the quarter, actually. Okay, other than the final exam for review stuff, but we're not going to talk about any more confidence intervals. We're spending pretty much the rest of the quarter going through hypothesis testing for different types of things, and also called regression analysis, which is next week. So just let you know, 0.05 is the level of significance, and do not confuse confidence intervals with hypothesis test. So if you want to state the conclusion, do not use the word confidence. That can't be done in this problem. Any questions on that? So we're going to let alpha equals 0.05 because it's a standard thing. Okay. So we did that. So the next thing you do, we collected the data. And again, I probably should have written this paragraph after, but I wanted to introduce. Okay, so when I did this in the real world, I was worried about them cheating at the very beginning, so I'd always check every time a new dealer came in. And then I'd wait a little while, watch it, and then if chi-squared failed, if the chi-squared rejected the null hypothesis, do you know what I would do, by the way? Do you think I would accuse them of cheating? Absolutely not. This is a mob. They kill you. You don't accuse people. You don't accuse a mob of cheating. You just walk away. Yeah, you just leave the room. You leave that table and you come back an hour later and hope they're gone. And they have their regular dealers. Yeah, no, you don't ever mess with the mob. Just let you know that. You don't fight them. Okay, so you just walk away. Very, very dumb to actually accuse them of cheating. But you walk away. So that's what you would do if you rejected the null hypothesis in this case. Whereas if you fail to reject, then you keep playing. So in a way, a type 1 error in this case would mean that you have decided they're cheating when they're not, and the repercussions, the damage done, is you leave, okay, or I leave personally. So what's the damage caused because I left when they weren't cheating in the first place? Doesn't hurt them that much. Doesn't hurt them at all, actually. Do you know the damage? Yeah, I don't win any money. Remember, I'm a card counter. That means I leave and I don't make the money that I expected to make because I drove all the way to Las Vegas to go play. Okay, so that would be a type 1 error. Okay, where a type 2 error would mean I failed to reject the null hypothesis. So in other words, I don't have evidence that I have a cheating dealer. And when they really are cheating, what happens then? Yeah, then I lose money because they're cheating, and I'm gonna keep playing when they're cheating on me. Okay, both are bad and both involve losing money. One is Opportunity cost, that's the type 1 error, means I had the opportunity to make money and I didn't. And the type 2 error is I lost money because I didn't recognize they were cheating and they just took my money. So they're both just as bad, actually. You lose money either way. Okay, that's why 0.05 is about the right thing to do. Any questions on that? Okay, so the next thing is we've got our data. And let me show you what we need to do with the data. This is going to be different than the other things. We don't have a mean, okay? We don't have a standard deviation. We just don't have that stuff. What we have in this case is we have what's called the observed and the expected. And what I'm going to do is I'm going to make a table. And it's an observed and expected table. And in this case, 4 by 2. So this is observed. And often they use O for observed and E for expected. Mathematicians are boring, so we just use whatever seems to make sense. So what we observed, if you look, and this is where you got to read the paragraph, is we observed out of the 80 cards, the dealer deals himself 11 aces. Okay, maybe I'm going to add a row, actually. Well, let me insert row above. Yeah. I'm going to write aces, face and 10. And other. And what we observed is 11 aces, 25 faces and 10s. And then there were 80 total. So we've already counted 36. So that means 44 left. Let me know if there are any questions on coming up with those numbers that are given in the question. Any questions on that? Okay, so now we need to do what's called the expected. Now the expected, there were 80 cards drawn, right? And I'm gonna do some rounding, by the way. How many aces would you expect if there's no cheating going on? What would be your best prediction for the number of aces if I got to see 80 cards? If it's truly random and no cheating. How many aces? How would we figure out how many aces? I don't see y'all jumping in. Okay. You say, well, there should be 1/13 of them being aces, right? 1 out of 13 cards are aces. So I'm going to do 80 divided by 13. And what it gives me is about 6. So I should expect 6 aces. Anyone lost on that? Because I would expect 1/13 to be aces. 1/13 of 80 is 6. Now let's do faces and 10s. So again, faces and 10s, 10, jack, queen, king, that's 4 out of 13. So if I go to my calculator again, and now I need to multiply by 4. So 4 times that. And I get about 25. And then other, well, now I've seen 31. So that gives me 49. Have I lost anyone there? Any questions on this example? All right. Well, did we get what we expected? Is the observed equal to the expected? What do you think? Okay. Well, more isn't quite the word. Remember, this is not a greater than or less than. what we look at are the numbers the same. Well, I see an 11 and I see a 6. I see a 25 and a 25. I see a 44 and a 49. Do we have the same numbers? And the answer is no. But this is statistics. All we have is a sample. When you have a sample, so you're not going to usually get exactly the same. So the question is, does it differ? Does the observed differ enough from the expected to be able to say that it was too unusual, so therefore we're gonna decide the dealer's cheating? Any questions on that idea? Okay. Probably very clear that if you looked at all 80 cards and they were all aces, then of course you'd say, yeah, the dealer's cheating. But if there's 11 aces and you would expect 6, well, is that far enough away from 6 to say the dealer's cheating? Or is that something that you would expect to happen? So what is the probability that these distances are as far or could be farther? So the distances from each other are as much or greater than what we got. So again, we got a distance of 5 between aces, between the observed and expected for aces, 0, and 0 is no distance for faces and tens, and 5 again for the others. And what we need to do is we need to say, well, you got 5, 0, and 0 as the 3 differences. Okay? And the question is, are those big differences or are these small differences? Does that make sense? All right, well, a couple things. Let me show you something. If we go to chapter 11, because I want to show you in the book. And again, we're over here, and we want to look at the chi-square distribution, because the chi-square distribution is going to be the chart that helps us understand that. I figured I'd show you a picture of it at least, but the one I programmed an interactive version. So it turns out there's degrees of freedom, and it depends on how big your sample size is, basically, to say what the chi-square distribution is. So here's the 1 degree of freedom. Here's 2. Here's 3. So if you have a bigger sample size, then it changes. If you have a very big sample size, what does it start to look like? What does that kind of look like? And by the way, that's a bigger sample size. Yeah, then it's starting to look bell-shaped. So the chi-squared actually becomes like bell-shaped if you get really big. But if you're not very big, it's skewed to the right. And by the way, the chi-squared is never negative. I'm not going to do the math, but there's a square going on. So it turns out it's never negative. And that's what the picture of the chi-squared distribution is. And for all of the tests we do today, we're going to be using this distribution. And I just wanted to show you the picture. We're not going to do much with the picture, but it's good to see that. Remember, a p-value, you're going to get a chi-squared test statistic. And the p-value, it turns out there is no left tail, right tail, and two-tailed, because you're either far away from the expected or not far from the expected. It's not greater than or less than. Does that make sense? So there is only one p-value that could even happen. You can't do a left or right tail test. And part of that is the chi-squared is always positive. There is no left. You only have a right tail. Because when you have a skewed distribution, you have a right tail. Any questions on that idea? Okay, so here we got, let me write these down because I'm going to need them. We have 11, 25, 44, 6, 25, and 49. Because I'm going to lose it in a second. So now we go to our calculator. So let's go to the calculator. By the way, I try to do it somewhat in the order of this class. And I mean, of how we do things. So you might even be able to guess, hopefully you can, given the names. I tried to make it easy. What calculator number do you think we're going to use? Yeah, it's 21 because we decided this was goodness of fit. And we want to type in the observed separated by commas. That was 11, comma 25, comma 44. The expecteds are 6, comma 25, comma 49. Any questions on that? And hey, calculate. I tried to make it easy. So what did we say? Our test statistic, by the way, you may not have seen this before, but chi, C-H-I is how you spell it, is a Greek letter. And it's a capital Greek letter, actually. And this is what it looks like. Kind of looks like a curvy X. So that's the way you remember chi. And it's called chi-squared. Again, math-wise, there's some squares involved. I'm just not going to go there. But what you have to know is just the name. Sound good? So the test statistic is the 4 points, I don't know, 4.7, good enough. So I'm going to write chi-squared equals 4.7. And the p-value was equal to about 0.01, 0.096. Any questions on arriving at the chi-squared and the p-value? Any questions? Okay, by the way, I'm trying to make the calculator easy to use. So if you watch my videos that use the TI-84 calculator, I spent a lot of time explaining how to use that calculator. So the good news for you is hopefully you agreed. Was that pretty easy to use this calculator? Put in the numbers and hit calculate? Yeah, so I tried to make it as easy as possible. If you have any suggestions, let me know to make it easier. But, you know, I have to use, if I don't have commas in between, then it treats it one big number. That's why you get out the commas. Because if I wrote 112544, then it's not going to know whether that's, 112,544. So that's why you need the commas. Just let you know. So that's a bit of a pain. You got to stick the commas in, but that's not too bad. And that's it. And there's your chi-squared test. And even though this is a new chapter, you've never seen this chapter, we've never done a test for qualitative data, and this is totally qualitative because the survey question is, what kind of card was it? And you're going to say, oh, it was an ace. That's not a number. Okay, it's a word, or it was an other. Do you see that? This is qualitative data, but we can handle qualitative data now. And yeah, if you copy the data, it's easy. But I purposely did the one that only had 3 numbers. I could do that in 5 seconds. But if you have a longer thing, then copy and paste is a good idea. So hopefully, even though you've never seen this before, you can tell me what to do when you have a p-value of 0.096 and, by the way, a level of significance of 0.05. And what is that? What do we do now? And I promised a couple weeks ago that we're going to use and reuse the same concepts. So here we are again. We have our alpha is 0.05. We have the p-value is 0.096. So what's your idea? You're all supposed to know this. This was on the test you just took. Not chi-squared, but alpha and p. So what do you do? If alpha is 0.05 and p is 0.096? I don't see y'all jumping in. Maybe I'll write it this way. So we have let's write P value is equal to 0.096, which is greater than 0.05, which is the level of significance. Yeah, so what we do is we fail to reject the null hypothesis. Any questions so far? Okay, we failed to reject the null hypothesis. So then here's the conclusion. The conclusion is I bet you can finish at least the next few words. What comes next after there? And by the way, when you took your test, I wanted to see that word there as the first word when I asked you to talk about your conclusion. That was important. So here's that word there again. What are the next couple words? After there. Okay, we've been doing this for weeks now. Yeah, I'm going to put the word is first, though. There is, but not significant. If you fail to reject, it's not significant, it is. Yeah, insignificant. Not un, but in. Oops. In. If you wrote unsignificant, I probably wouldn't take any points off because that's just grammar issues. Evidence. 2. Conclude. And I like to write whether or not. That way you don't have to even think anymore. Once you write whether or not, you're pretty much saying you don't know anything. And now what I can do is I can go to the null hypothesis or the alternative hypothesis. It doesn't make any difference because I wrote whether or not. So I'm just going to use the null hypothesis. It sounds a little better. And just copy and paste and change that T capital to T lowercase because it's in the middle of the sentence. So let's read it. So there is insignificant evidence to conclude whether or not the distribution of the dealer's cards is the same as a distribution for the regular card deck. And that's it. So by the way, do we keep gambling or do I leave? What do you think? You keep gambling. Does this mean the dealer's not cheating? Yeah, the answer is we still suspect they could be cheating. We just don't have the evidence yet. So what you do is you keep gambling, but you keep tallying up. And if it gets to a p-value that's less than 0.05, you get out of there. Got it? Okay. And you could go 0.1 if that's, if you were more worried about cheating, but that's up to you. Okay. And of course, the hard part is, by the way, calculators were not allowed in the casinos. I'm not sure about now with smartphones, but in those days, you were not allowed to bring a calculator. So I had to do all this in my head. And trust me, I'd be tired at the end of the day, but tired and rich, which is always good. Okay. So that was my story. Okay, any questions at all on this example? Any questions? All right, so the next thing is I want to do, I only have enough time to do a little bit, but I want to mention another example that would happen. I'm not going to go through the whole thing because I got to do the other two types. And that is, let's suppose you wanted to find out, maybe you're a believer in astrology. You know what astrology is? Hopefully you do. Okay, astrology is the idea that the month you were born on, okay, or the moon you were born at is really what it is, because it's the moon lunar calendar. Will help you decide your life. I'm not sure if you realize that, but that's kind of what astrology is. And let's suppose you want to find out if it's true. Okay, and maybe you want to look at, let's say, you want to say, well, how about people who are divorced or not? Okay, well, maybe if you're under the right moon, then your marriage is likely to be, going to make it. Whereas if you're not under the right moon, maybe it's not. Okay, so you might want to say, well, if you look at the divorced people, and you want to find out, if you look at divorced people, is the distribution of the astrological symbol uniform? Or are there some astrological symbols where you have like not much of a chance? Does that make sense? So what you would do is you would survey a whole bunch of divorced people, ask them when they were born, what their astrological symbol was. And that would be a chi-squared good as a fit test. And the H naught would be the distribution of astrological symbols amongst divorced people is uniform. Because if it's all the same, we use the word uniform. Do you remember that? So again, I don't have time to go through the calculations, but basically it looks just like this. And in the expected, all you do is you take the sample size, and I'm not sure, I think there's 12 astrological symbols, you divide by 12. And every sample size would be the same because that's what uniform means, is the same. Any questions on that? Okay, I don't have time to do examples of everything, but that would be an example when the distribution is uniform, and that comes up some. Okay, now I want to go into a different type. So let's suppose you did a Likert scale for, except that's not how you spell scale, SC, for men and women. Asking them how much they liked working at home instead of having to go to work. I think it's a U, Likert. Oh, it's capital. Okay, who knows what a Likert scale is? This is a psychology thing, not a math thing. Anyone heard that word before? Because they wanted me to capitalize, it's probably a person's name, Likert. You've all seen it, you just haven't seen the word before. Okay, it doesn't have to be personality, but the idea is that it's a question where it is the following, and there's different types. I'm gonna do the 4-point Likert scale, where there is strongly disagree, disagree, agree, and strongly agree. That's called a 4-point Likert scale. You've all seen that before, right? You have a survey question and you have to answer one of those 4 things. Okay, notice it's qualitative, it's not quantitative. A 5-point, by the way, in the middle, you have neither agree nor disagree. So those are the 4-point and the 5-point Likert scale. Again, this is not a math thing, this is psychology, but it comes up a lot. You see these on surveys all the time. And what we want to do is we want to say, is there a difference between men and women? Okay, so is there a difference between men and women on how much they like working at home instead of having to go to work? Okay, given the fact that right now, right now, I'm working at home. My cat's very happy. She's right over here. Do I like it? I don't know. I think I like going to work. But I'd have skied to work for my commute this morning, by the way. So but that's the kind of question you can ask. So in this case, let me give you the results are shown below. So the survey was done. So the first thing is you don't have to ask the same number of men and women. You could ask, 100 men and 80 women, or 150 women and 120 men. It doesn't matter. You do need a sample size so that all the expected counts are bigger than 5. So just like the yes, no, you have to have bigger than 5. So for example, we had these expected over here, 6, 25, and 49. And those are all bigger than 5. So that means that we can actually do this test. Whereas if you don't have bigger than 5, you can't do the chi-square test. So just to let you know, that's what the sample size issue is here. So now I'm going to make a table. And there's a 4-point Likert scale. So let's insert a table. And like that. We're going to have men. We're going to have women. And then we have, I'm going to write SD. So I'm going to type the whole thing. Strongly disagree, disagree, agree, and strongly agree. Hopefully you're all okay with my abbreviations. And let's suppose we asked a bunch of women and a bunch of men whether they agreed or strongly agreed with this question. Okay, do you like working at home? Or I guess I like working at home instead of having to go to work. And you could say strongly agree, disagree, strongly disagree, agree, etc. And let's suppose these were the numbers: 56, 140 or 150, 120, and 80. And let's say the women had 28, 49, 160, and 98. Okay, and what I should do is I should write H naught. And I want to let you know. Oh yeah, so you asked if it snowed. Yeah, no, it snowed a foot. It snowed a foot yesterday. It was beautiful skiing yesterday. I'm going to ski this afternoon too. Just to let you know that, off topic. But I see you asked. Yep. Okay, so H naught is now, what word did I tell you needs to be there for the last chi-squared test? Who remembers the word? Yeah, distribution. Now, the only difference for this kind is it's not going to be distribution. It's going to be distributions because we have men's distribution and women's distribution. So the distributions of answers to the survey question are different, or are the same, sorry, for men and women. Any questions on that? Okay, so the distribution of answers is a survey question because that's what we're looking at. Are men and women, are they the same, or maybe they're different? Okay, and the good news is I can copy and paste H naught into H1, but I need to make an adjustment. And what adjustment do I need to do for H1? Yeah, I can add not. I'm going to do a little differently, but I can add not if I want. That's fine. It's a little easier. But I like to get rid of the same, and I write different. I know it's a few more letters than the word not, but it sounds better. So the distributions of answers to the survey question are different for men and women. Any questions on that? Okay. This is not a goodness of fit test. This is not a single sample at which you're comparing some known distribution. Here we have men's distribution and women's distribution, and we don't know either of them. So we cannot use a goodness of fit test. Got it? So the test we're going to use will be a chi-squared, still chi-squared, test for homogeneity. Okay, and you may or may not know the word homogeneity. It's not a math word, it's an English word. Anyone heard that word before? You've probably seen it under homogenized milk, for example. Yeah, homogeneity means the same. So same distribution. We're testing to see if the distributions are the same. Any questions at all on that so far? Okay, so now let's see if it'll do it for me. I'm going to try. I think it will. I'm going to copy just for later. Let's go back to the calculator menu. This is not goodness of fit, so we can't use a goodness of fit test. But it should be obvious. What number do I use? Yeah, this one's 23. By the way, there are 25 calculators here. We're doing 21, 22, and 23 today. So what does that tell you about this class? Yeah, it's almost over. Okay, we're getting towards the end of this class. Just to let you know that. Okay, we spend a whole week on calculator question 24. And 25 is, yeah, we have a chapter on that, but it's actually, I only spend half the lecture on that because mostly I just review for the test, for the final. So just let you know, ANOVA is a quickie. So we're almost done. Okay, we're very close to finishing. But we're going to use test for homogeneity. And what it says is enter the observed values for the two samples A and B. So this isn't a comma one. Sorry about that. Okay, then hit calculate. And it'll give you the p-value. So I do need the numbers. Let me go back, write them out. So 56, 150, 120, 80. And then for the expecteds, we have 28, 49, 160, and 98. Okay, and by the way, you're not usually going to have a lot of choices. So it's not like you have a zillion numbers to write. That's why I think I didn't do the commas, because it's good enough. Okay, leave the rest blank, it says. I think it says, but yeah, leave the rest blank. We go in and we hit calculate. So chi-squared, 61.89 about. This time I'll type it in just for fun, because you can actually do it. So chi squared equals 61, was it 0.89? I'll find out in a second. Yeah. Okay, is the p-value 2.31? Do I write that down? .3. Yeah, it's not 2.31. So be careful. P is a probability. It is never bigger than 1. Don't ever, ever, ever write P equals 2 point something. It can't be. That E negative 13 means it's got 12 zeros before the 2. So that's our P value. There's our P value. It's not 2.31. It's this really ridiculously low number. And I will let you know, in the real world, when you do a survey, many, many times you get P values that are this small, okay? Or the opposite, they're really big. And the reason for that is if you think something's true, and it really is true, and you do a big sample, you're gonna get a tiny P value, okay? That's just the way it is. So what can we say? So what's the conclusion? How does it start? Yeah, there is. And I'm going to put the word strong, maybe even very strong, because we have a really small p-value. So you like to brag when you got that. Very strong statistically. Statistically significant evidence that and now, oops, it's over here. It's H1 that you always find evidence for. Make that T lowercase, that the distribution of answers to the survey question are different for men and women. So it means that men and women do not feel the same about the liking the fact that they're working at home instead of having to go to work. Okay, they don't. Does this tell you who likes going to work at home, being at home for work better? Okay, the answer is no. And I want to mention, I'm gonna say this a lot in this class for the last few weeks. Does that mean you can't ever find out? What do you think it takes to find out more than just there's a difference, but actually how they're different? What do you think you have to do? And it's going to be, for now on, there's going to be a common thing I'm going to end up with. Should I tell you? You need to take another statistics class. Okay, you don't get it in elementary stats. You need to take advanced statistics. And then there is a way, and it's called Tukey analysis. But again, we don't do that in this class. What we do is we stop basically here. Okay, we just say, yeah, there's a difference, but we can't say where the difference is. Does that make sense? But we can say they're different. Any questions at all on this example of a chi-squared test for homogeneity? Very good to find out if you have two groups and you want to compare the groups and to say, is there a difference from one group to another, or maybe not? I want to mention one more big application. A lot of times what you're going to do is you're going to do a big study. Okay, and it might be a very expensive big study. And what you often do is you do a preliminary study first with a smaller group. And one of the things you might want to do is you might want to study on this, do people, forget men and women, but do people, how satisfied are people with working at home? Does that make sense? And what we did in the first week, which I say a lot, is we talked about sampling techniques. And one of the techniques I talked about is stratification. Do you remember that? So in this case, stratifying by gender is something you probably want to do, because what it'll do is it'll take away gender bias. And when you have a difference between men and women, then you don't want to ask more men than women or more women than men. On the other hand, if we had a p-value of 0.9, then you would say, well, maybe stratifying by gender is not that important. Maybe I should think of other things to stratify by, because maybe it doesn't matter whether it's a man or a woman, they're the same. Do you see that? Or they could be the same. But we just found out they're not the same, which means you got to make sure that you're stratifying by gender. Any questions on that idea? So a lot of times this test for homogeneity is used to decide how to do the larger study in terms of what to stratify by. All right, now let's do the last type. Suppose you wanted to find out if ethnicity is a factor in choice of major for college students. Okay, maybe it is, maybe it's not. Okay, but you want to find out if it is or isn't. Any questions on the idea first? Okay, so in other words, does it matter which gender, which ethnicity you are when it comes to major? Okay, and so here is our H naught. And that is, there's a few ways of wording it, but let me give you the word that you need on this one. And that is ethnicity and major are independent. And H1, I am going to copy and paste. You're used to me doing that by now. How do you think I need to change it? What do you think? For H1, what adjustment should I make? It's a small adjustment in terms of easy to type or untype. Any thoughts? I don't see y'all jumping in. Hopefully you can hear me. It's not a trick question. So H1, what should H1 be? It's not going to be ethnicity major or independent. It's a small adjustment. And what is that small adjustment? Yeah, the IN goes away. So H naught is ethnicity and major are independent. H1 is ethnicity and major are dependent. And that's it. Any questions on H naught and H1? Okay, the test is a chi-square test. And now it's called for independence, because we want to find out if they're independent or not. So by the way, I'm going to do some highlighting. Independent and dependent. Those words need to be there in H naught and H1. Got it? Okay, so now suppose a survey was done of college students. And I'm going to simplify just so I can type less. Otherwise, it'll take all day for you to watch me do this. So I'm going to insert a table. How about 4 by 4? Did that work? Oh, it went on 2 lines. I want to go on 1 line. That was the issue. There we go. Or two pages. There we go. Okay, so suppose I'm going to limit the choices. I'm going to just say STEM, humanities, and other. And then at least at LTCC, there typically is Caucasian. There is Latinx, I think is how you say it. And then let's call it other. Okay, in the real world, you'd probably have more ethnicities you write down and probably more majors, but I don't want to spend all day typing numbers in if that's okay. So this is just to show you how these things kind of look. And let's suppose we get the following numbers. So there were 72 students that were Caucasian and said they were STEM majors. 76, sorry. There were 89 Caucasians that said they're humanities. And there were 47 other majors. For the Latinx, there were 83 for STEM. There were 90 humanities and 46 other. And then for the other races, there were 23 STEM. There were 20 humanities. And there were 12 others. Any questions on the table? Okay, so again, I think I've already said it. We're doing a chi-squared test for independence. And let's just let alpha, I think I'm even going to say it. Usually an alpha is not given. And what you do is you just kind of use strong statistically significance, or weak if it's between 0.05 and 0.1, or insignificant if it's greater than 0.1. Sometimes you just use language. So I'm just going to use language on this one. So now we got to go to our calculator. As always, let me put these numbers in. 76, 89, 47, 83, 90, 46, 23, 20, and 12. So now I go ahead and go to my calculator. Let's go back to the calculator menu. Okay, so what calculator number are we going to do? I tried to make it easy. Yeah, this is 22, test for independence. So I really did use the names of these things when I named them. And this is another one where, you know, I just called it first, second, third, fourth, fifth, sixth, seventh. There's like an A, B, C, D, or something like that. And leave anything blank if you don't have that many. So our numbers were, do I have them all? I don't think I have them all. Just a minute. Oh, there they are. A different place in my paper. Okay, so our numbers were 76, 89, 47. Then there was 83 and 90. And 46. And then there was 23, 20, and 12. Okay, and I want to let you know there's observed and expected here. You need to make sure all the expecteds are bigger than 5. In this case, we're okay. And you can just trust me on that. And then we just go recalculate. Okay, we get a chi-squared of 0.84 and a p of 0.93. The p-value is 0.93. Okay. Do I need to know a level of significance? What do you think? Do I need to? I didn't write down an alpha. Do I need to give you an alpha? What do y'all think? Yeah, definitely not. Look at the p-value. P-value is 0.93. You're never going to have an alpha bigger than that. Okay, 0.1 is the biggest we ever do in this class. Forget 0.93. So what we can say is there is statistically insignificant evidence to make a conclusion, whether or not. And then I just do a copy and paste. And it doesn't matter which one I copy if you say whether or not. It matters if you do have evidence, then you need to copy H1. But with the whether or not, that gives you both H0 and H1. So ethnicity and major are independent. So we don't know, okay? But our p-value is so big that we're not even going to even think about doing another study. We're going to say it just looks fine, okay? I want to let you know, this is important. I made up these numbers, okay? Don't tell everyone, oh, I just saw a study done and it said that, we had a p-value that was 0.93, so there's no relationship. I totally made these numbers up. I have no idea. But a study could definitely be done. It wouldn't be a hard survey to ask. And again, in the real world, you'd probably have more categories, but I didn't want to spend all day typing. So, but in the real world, you don't mind spending an extra 20 minutes typing if you're going to spend, many, many hours on a study. Any questions on this idea that the chi-squared test for independence? Here's a question I have for you. What do you think the hardest thing about this chapter is when it comes to the final exam? Wording's not that bad, actually. Especially you get a note sheet. Yeah, knowing which calculator to use, which test to use. That's where people go wrong. Okay, you need to know which test to use. So chi-squared test for independence is when you have two survey questions, both are qualitative, and you want to find out if one is a factor in the other, and that's it. Okay, and in fact, sometimes you'll see that sometimes instead of statistically significant evidence to make a conclusion whether or not ethnicity and major are independent, sometimes you'll see instead you would say there's statistically insignificant evidence to make a conclusion whether or not ethnicity is a factor in major. In what major students choose. Okay, so that's another way of saying the same thing. Okay, the wording's not that hard, actually. What's hard is to know which one to use. We have a lot of different types of hypothesis tests already, and we still have 2 more to go, just to let you know. These are the only ones that are qualitative, though. So today is a qualitative day. Okay, I want to mention a few things, very important, especially after I graded some of the tests already, about the project. So if we go to the syllabus, I'm going to mention a few things to worry about. So in terms of timeline, so already in the past, you should have found partners. That should have already happened. If not, you need to get partners now. Okay. So that's the first thing. It already happened. Second, and you should do this as soon as you can, come up with your H0 and H1 survey question and how you're going to survey or how you're going to collect the data. It doesn't have to be a survey question, just be data collection. But you're not going to find someone else's paper and analyze their paper. You could find someone else's data if they didn't analyze it with a hypothesis test. That you can do, or you can find data from some website. That's allowed. Okay, you can't, if you can get the whole population, then it's not okay, because there's no reason to do a survey or a hypothesis test or a confidence interval if you know the whole population. Okay, so that's just a couple notes. I want to mention a few important things about Project 2. One, and it may or may not say it in here, but don't make it look like the answer to a test question. Okay, a test question, you only have, 2 hours to the whole thing, so we're talking about 10 minutes a problem. Here you're doing one problem and spending days on it. So don't just give one sentence interpretation of the conclusion. Make it a full paragraph conclusion. Similarly, don't make the p-value interpretation look like just a test question answer. Talk about why the client cares, what it matters, how it relates to the standard error, for example. Okay, so again, don't make it just look like a homework assignment, okay, or a test. The other thing is the word population should be in many places in your study. So same thing with the exam, by the way. Unfortunately, a lot of you didn't put it in. Is that if you are talking about the population mean, you must have the word population there. Otherwise, I'm going to assume that you're confused. Got it? So these are just some things that people make mistakes on. So you should go ahead and get your hypotheses posted on the Project 2 discussion board. I'll let you know if it's going to work, and if not, what modifications need to be done to make it work. I recommend at least collecting one data pair. And if they're not numbers, then it's not okay. This is quantitative. So it's a mistake people make, is it has to be quantitative. So you look at your data, it should be a bunch of numbers that you're going to be typing in 2 columns into the computer. So make sure that it's quantitative. I'm just going through the things that people make mistakes on at the beginning. So any questions at all? I think I'm going to stop my share. And I'll be around again Wednesday. I won't be checking much because it's a holiday. But other than that, I'll be around a lot. I'll check a little Wednesday, but for many hours I won't. And this week you do have a discussion assignment, so don't forget to make that happen. Last week you didn't because of the test. This week's a light week. And the secret word for today is distribution, because distribution was a necessary word in hypothesis testing for goodness of fit. If you don't use that word, you will lose points. So secret word is distribution.